Welcome to Sigma Solver, guys. Before I start the video, I want you guys to smash the like button. This helps the YouTube algorithm and keeps me motivated. And if you are new here, then subscribe to my channel and press the bell icon so that you never miss an update. So without any further ado, let's get started. Today we are going to look at a new topic which relates to global neighborhood and local neighborhoods as well in a graphical data scenario. So let's read the question first. Use Katz Index to find the number of paths of length 2 between the vertices 2 and 3 in the given graph. So the question by itself doesn't have a lot to say. It just asks to find the number of paths of length 2 between 2 and 3. So consequently it is this path, right? And it's that simple. But the thing which we will discuss today is more towards what is Katz Index and how can we use it to find meaning with respect to a global neighborhood. I know the word itself doesn't make much sense because neighborhood is something that we see in a local scale, but then it's attached to the word global. So first we understand what is local neighborhood based features. It says when two nodes in a graph have one or more common neighbors. So in the above example, we can say that 1 and 2 are neighbors. Why? Because they have 4 as the common neighbor. Next, they are better than distance based features because they fail to highlight clusters. So distance based features are like what is the maximum path length in the graph, what is the diameter of the graph, what is the average path length between the two vertices. All these are distance based features. So they are good to approximate the entire graph on a Euclidean metric system where the distance is sufficient for the problem statement. But when we are concerned with the network patterns and want to predict which particular node will bind another node from a different graph, then we might need something more related to clustering and helps us identify the characteristics of a community or subgraph. So that is why local neighborhood based features are more popular these days. The last thing is the limitation. So the limitation is that it fails to provide information if common neighbors are 0. So it might be possible that a few of the nodes have the connections, but we are missing some important links between these interconnections only due to the fact that they have no common neighbors. So this is an example of graph that I am trying to explain. This is a single graph where there are two vertices that we are focusing on, V1 and V2, and there are other vertices as well. So V1 and V2 will exhibit very similar properties because of the structure that they possess around them, but since they have no common neighbors, so local neighbor based features would not identify them as having high similarity. So this is the problem that on a small scale doesn't feel much because there is only a path length of 4 nodes to cover and then we'll land up on the next similar node. But for larger graphs where thousands of nodes are there, similar structures are more than difficult to identify using these features. So that's why this is a limitation. Now we will see that how global neighborhood based features are going to identify the loopholes and then fix them. So as the first point says by itself is it studies the entire graph. So it takes into account the entire graph before dissecting it into similar or dissimilar node structures. The first element that we'll look into in global neighborhood based features is Katz Index. So it counts the number of paths of all lengths between a given pair of nodes. So generally Katz Index is referred to with respect to a pair of nodes, but later on we will see that we can identify Katz Index on a matrix level or a graph level as well. So the idea is to use the exponents or power of the adjacency matrix in order to find the Katz Index. So the adjacency matrix for the given graph, which was there in the question, is going to be this. This is simple. If there exists an edge between I and j, then its value is 1, 0 otherwise. So simply put, the next thing that we go for is we let the number of paths of length 1 between 1 and 2, for example, as P1, 1, 2, P1, 1, 2. Note that 1 is in the superscript and 1, 2 is in the subscript. We observe that it's equal to A12 or A21. But this will be different in the case of a directed graph, and because in that case 1 to 2 might be 1, but then the opposite direction may not be present in the graph. So then this might not hold, but this will hold in either cases. We will also see later in this discussion that how weighted graphs can also play a major role in fractional powers of adjacency matrix to derive the number of paths between them with that same weight. So now we want to compute P2 of 1, 2. So the naive approach for this is identify the count of the number of paths of length 1 between 1 and all of its neighbors. So at this point, it is quite clear that we are going for an approach that is having an n square of time complexity. The next step will be we take 1's neighbors which we have identified in step 1 and find the path to the node 2, and that should be of length 1. So now we are looking at the first length which was 1 by default, and the next length which we are filtering out as 1, which combines to 2, which was asked in the question. So mathematically, if we try to define it, it will be P2 1, 2 equals to summation of I over all the nodes A of 1i times P1 of I2. So what does this mean is that we are going to traverse the entire neighbors of A in the adjacency matrix where it has a link to the node, and that will be multiplied to those nodes if they have a connection to the node 2. So we just put this using the inference 1 that we had put previously here, but this, if we closely look into, we are going to traverse the rows, and then for each row we are going to traverse the columns. This is going to traverse the rows and this is going to traverse the columns, and in this fashion we can see that we are actually going for A square in the matrix form. So then we understand that via matrix what we are trying to achieve is that first we take the neighbors of node 1. So in the first row we will see that those connections where 1 has a node neighbor is 2 and 4, right? Then for the second matrix we see that if this particular nodes that we just saw in the previous matrix, that is 2 and 4, do they have a connection with node 2? So for node 2 there is no path, which is obvious because the graph doesn't have a self loop. Next, for node 4 we see that there is a path to node 2 of length 1. So finding 1's neighbor has a path length of 1 to node 2. Now what we can see that if we multiply these two matrices, because they are both conformable, 4 cross 4 and 4 cross 4 again, so we will get a 4 cross 4 matrix of A square. In that the row 1 and column 2 will be of value 1, indicating that there exists one path of length 2 from node 1 to node 2, and since this is an undirected graph, it will be vice versa, means equal to P of 2, 1, 2, right? So the deduction that we get from here is that A of UV in the adjacency matrix tells us about the direct neighbor of a node. A square tells us about the neighbor of the neighbors of a node. Similarly, A raised to power L will tell the number of paths of length L between node U and node V, right? So then we formally define the Katz index. It is a metric that measures the global neighborhood overlap. So right now we can see that for each node there will be an overlap based on the number of paths of length L it will have to that particular neighborhood. So if we put it mathematically, it will be the summation of all path lengths from 1 to infinity beta raised to power t A of V1 V2 raised to power t, where the second term is the number of paths of length t between V1 and V2, and beta raised to power t is a discount factor that lowers the importance of large path length. So we can see that when t becomes large, A raised to power will also probably become large as well. So to normalize that effect on the Katz index, we put this discount factor which lies between 0 and 1, and as t increases the entire value of this term will decrease, which balances that out. So this is the Katz index that we are going to find with respect to node V1 and V2. Now we observe that since this becomes a converging geometric progression, its value can be approximated to a fixed value, because beta raised to power t always diminishes and a raised to power t V1 and V2 might remain the same or increase in value. So this leaves us with Katz index for the entire matrix concerned, which is equal to I, that is identity matrix, minus beta times A whole inversed minus I, where the first term is nothing but summation of I equals 0 to infinity beta raised to power I multiplied A raised to power I. So that's how we formulate the global neighborhood overlap for a given graph using Katz index. This not only overcomes the limitation of having unnecessary common neighbor, but provides essential characteristics to local clusters as well as global connections. So that's been it. If you still have any doubts, then feel free to reach out in the comment section below. If you liked this video, then give it a thumbs up and subscribe to my channel for the upcoming videos. Till then, happy solving.
Hey there, before you go, I've got some fantastic content lined up for you. Over here, we've got some videos and playlists you might enjoy. But first, if you haven't already, make sure to hit that subscribe button and ring the notification bell so that you never miss out on any of our future uploads. Thanks for watching, and I'll catch you in the next video.